Welcome to today's YouTube tutorial on mesh analysis. If you are looking to master the art of analyzing complex electrical circuits, you are right in place. In this tutorial, I will deep dive into the world of mesh analysis, breaking down the fundamental concepts, the techniques, the strategies you need to effectively solve circuits with multiple loops. In the last two tutorials, I explained what a loop is and what a mesh is, what a node is, what a branch is. Whether you are a student, an aspiring engineer, or simply curious about circuit analysis, this tutorial will equip you with the skills to confidently tackle intricate circuits. So let's get started and unravel the mysteries of mesh analysis together. Last tutorial we talked about nodal analysis, and we said that nodal analysis is the way or is a method of analyzing circuits that have multiple nodes. KCL is only applied to just one single node, like we did in our first tutorial on Kirchhoff's law and Kirchhoff's current law and Kirchhoff's voltage law. But nodal analysis is applied to circuits involving multiple nodes. 3, 4, 5, 6 nodes. Mesh analysis too is a method applied to circuits with multiple loops. In our first tutorial, we only talked about a single loop. We only applied KVL to a single loop. But in this case, we want to see how we can solve a circuit that involves multiple. You can have like 4 loops, you can have like 5 loops. How do we solve for an object of interest in that case? So that's where mesh analysis comes into place. And just like our last tutorial, we did supernode analysis, and here too we will be treating super mesh analysis. In nodal analysis, we said that the supernode occurs when a voltage source appears in between two non-reference nodes. But in super mesh analysis, we say that it occurs when we have a current source in between two loops. A current source in between two loops. So that's where when mesh analysis comes into place. So the difference between mesh analysis and nodal analysis in the sense that nodal analysis can be used to solve any type of circuit. It can be used to solve planar and non-planar circuits. Planar circuits are circuits that can be drawn in a plane, right? For example, a physical circuit in a place that you can attach it to the wall and you still see how the circuit is going. That's a planar circuit. But a circuit that you see that it's not every part or not every branches can be joined to a wall, it will disfigure the orientation of the circuit, right? A planar circuit is a 2D circuit. A non-planar circuit is not a 2D circuit, right? So nodal analysis can be used to solve any type of circuit, planar or non-planar circuits, but mesh analysis can only be applied to planar circuits. Right, it can only be applied to planar circuits. So a circuit in which you see that the branches are overlapping, so that's a non-planar circuit. It's not planar because, well, in this case, in planar circuits, branches cannot overlap. If they touch each other, it means that they will form a node at that point. But when they overlap each other, it's not a planar circuit again, and of course mesh analysis cannot be applied. So that's one advantage of nodal analysis over mesh analysis. So we already talked about paths, closed paths, and loops in former videos, and you can check them out. The first video in this playlist, and you see how the definition of paths, the definition of loop. Of course, a path is a substance that has an electrical component, right? A branch that has a branch. Of course, we have a path is a movement of current where more current moves. So if where the current starts to enter a particular electrical component and the current ends at the same particular point, that's what are known as a closed path. For example, let's say the current is entering here, let's say, right, we have a resistor here and maybe an inductor here and a source here, and the current still comes back to this point. So that's a closed path. But if it is not closed, that is, maybe as this coming here, right, it goes down, and maybe it's open, right? This is not a closed path, it's just a path, right? So that is a path and a closed path. But what is a mesh? A mesh is a loop that does not contain any other loops within it, right? So look at this circuit here. right? So this is a mesh. This is another mesh. This is another mesh. This is another mesh, right? Because it does not contain any other loop in it, so it can be called a loop, but a loop is a general name. Whether it has another loop in it or not, it is called a loop. But a mesh is a loop that doesn't have any loop inside it. So from here, from this point, if I move around here, it is also a loop, right? This loop here is also a loop, but it's not a mesh because it has two loops inside it. It is not a mesh. So that is the difference between mesh and a loop. In this mesh analysis, we will be applying KVL, the Kirchhoff's voltage law, to solve our circuit. In nodal analysis, we applied Kirchhoff's current law, but here we will be applying Kirchhoff's voltage law. So let's look at an example. So this is an example, and in nodal analysis, we usually apply nodal voltages. For example, if I want to use mesh analysis, if I want to use nodal analysis here, although this we just have a case here because I only have two, sorry, I have more than two. I have more than two nodes. This is a node, right? This is another node here. This is another node here, and this is another node. So I have four nodes in this circuit. So if I'm to use nodal analysis, I'll just have to put this as my reference node, and of course use this one as V1, V2, and V3. But here I want to apply mesh analysis, right? So in nodal analysis, we apply we designate nodal voltages, but here we designate mesh currents. You can see the difference: nodal voltages, mesh currents. So right, so in this mesh, we say that there is a mesh current, and let us name it I1, and here we have I2. We have I2. So we have I1 and we have I2. So, and of course, we apply KVL at each mesh. So remember, in nodal analysis, we apply KCL at each node. But another difference between nodal and mesh analysis, there's nothing like reference mesh here. Everything is mesh, and there's no difference between any mesh. So we have two meshes, and therefore we should be expecting two independent equations, right? Two independent equations. So applying KVL to mesh 1, applying KVL to mesh 1, so we have to apply KVL to this mesh here, and you can see the direction of current. Direction of current is clockwise. So when it gets to this 42 volts, it is entering through the negative. So right, to the negative terminal. So that's minus 42 volts. Minus 42 volts. Right, then when it gets to 6, remember we are applying Kirchhoff's voltage law. So the voltage drop on 6 will be what? 6 times I1 using Ohm's law. So plus 6 I1, and when it gets to 3, the current on 3 is what? I1 and I2 are affecting 3, right? So since we are going clockwise, I1 is going in the same direction, but I2 is going in opposite direction. It is going anti-clockwise. So I2 will carry the negative. So by Ohm's law, it is resistance multiplied by current. I1 is having the positive, minus I2 is carrying the negative, is equals to 0. And that's it. So if you have to rewrite this, we have 9I1 minus 3I2 equals 42. And of course, I can divide this by 3. I can divide this by 3 to give 3I1 minus 1I2, or let's say minus I2 is equals to 14. So that's equation 1. So applying KVL to mesh 2, what do we have? Now we are going clockwise from I2. So when it gets to 3 ohms, I1 will be going clockwise too, but this is going up, I1 is going down, right? Since we are going up using the direction of I2 we have the positive. So 3 into bracket I2 minus I1, that's the voltage on 3, plus 4I2 minus 10 equals 0. So if I'm to rewrite this, I will have minus 3I1 plus 7I2 equals 10. That's equation 2. You can see that we have two simultaneous equations here. We have two simultaneous equations, and these two equations will help us to get what our mesh currents will be. So with this mesh currents, we can use it to get so many other variables. For example, I can get the voltage on 6 ohms by multiplying 6 with I1. I can get the voltage on 3 ohms by multiplying 3 into bracket I and subtract multiplied by the difference between I1 and I2, right? I can get voltage on 4. I can use it to get different variable of interest in this circuit, right? So if I solve this by using calculator, I will have I1 is equals to 6 amperes and I2 equals to 4 amperes. You can confirm this using your calculator. So you can see that that is very straightforward to get. Let's do another example before we go into the super mesh analysis. There are different types of sources we have, right? We have dependent sources and independent sources. This is the symbol for dependent sources. So they usually have a circle notation. So if it is voltage source, it will be like this, and if it is current source, it will have an arrow to show the direction of current. So these are independent voltage and current sources. They don't depend on any variable. But we also have dependent sources. Dependent sources have the diamond shape. So if it is voltage source and if it is current source, so what do they depend on? They either depend on voltage or current, right? So this is a current source. If it depends on voltage, you will say that it's a voltage controlled current source, right? But if it depends on current, we say that it's a current controlled current source. This one, if it is dependent on voltage, you say that it's voltage controlled voltage source, and if it is dependent on current, you say that current controlled current source. So sorry, this should be C. Sorry, current controlled voltage source. How do I know how it is controlled? Whether it is controlled by voltage or controlled by current. So if I have a source like this, plus minus, right, and I have 4I, so what does that mean? It's depending on current. So that current is a variable or in another part of the circuit. So it is depending on current, and therefore it's a current controlled voltage source. It's a voltage source, but it is controlled by this current I. So I believe you understand how we name these dependent sources now. So let's do an example that involves dependent source. So we use this example to illustrate how we will simplify it, how we simplify a circuit using mesh analysis, but this circuit involves dependent source. So as usual, we'll assign mesh current. So let me name this I1. Sorry, I have to name this I2 because there's already I1 here, right? So this is I2 and this is I1. So mesh I1, applying KVL to mesh 1. So mesh 1 gives what? If it when it is entering 3. When it is entering this source, we have what? 3. Then when it gets to this 4, we have what? Plus 4 to bracket I1 is going in that direction, but I2 is going in opposite direction, right? Then plus 2 I1 equals 0. So if I should write this, I should have 6 I1 minus 4 I2 equals minus 3. That's equation 1. So mesh 2. Mesh 2, we have, when it gets to 4, we have what? 4I2. So when it gets to 5 volts, the voltage source there, we have minus 5. It is entering through the negative, right? When it gets to this dependent source here, it's also entering through the negative. So that's minus 4I1. Then when it gets to this 4 here, right, we have what? 4I2 minus I1. Remember that the reason why we wrote 5 and 4I1 here is because they are already voltages. So we don't need to multiply it by I2 or anything. So they are already voltages. But this resistor, they are resistance. For us to get voltages, we have to multiply it by the mesh current, and which is equals to 0. So if I should write this, I should have minus 8I1 plus 8I2 equals to 5. That's equation 2. So I want to believe that you get and you understand how I got these two mesh equations. Solving these two simultaneous equations, we have I1, we get I1 is equals to minus 250 milliamperes, right? And I2 is equals to 375 milliamperes. So that is I1 and I2. And of course, if you want to get the voltage here on the dependent source, that is the real value of the voltage source, it will be V is equals to 4I1, right? So which is what? 4 multiplied by minus 250 milliamperes. So that will give me minus 1 volt. That's the voltage of the dependent source. That is as simple as that. I hope you understand. So the steps once again is determining if the circuit is a planar circuit. If it is a planar circuit, you can apply both any of mesh analysis or node analysis. But if it is a non-planar circuit, perform node analysis instead. Then okay, if it is a planar circuit, the next step is to count the number of meshes. Right? So count the number of meshes, then label each of the meshes with a current. That is, designate mesh current to each meshes. After that, the next step is to write KVL equation around each mesh. That is very, very simple to understand. Then the next step is express any additional unknowns such as voltages or currents other than mesh currents in terms of appropriate mesh currents. So this is just the example we did here. So the dependent source is an additional unknown. So we have to express it in terms of the mesh current, which is 4I1. Right? Then organize your equations and solve the system of equations for the mesh current. That's very, very simple. If you have any question on what I just explained, please drop a comment on this video and I will give you an answer in the comment space. Okay, let's talk about super mesh. This is an example we use to explain super mesh. Like I said, super mesh is what? When we have a current source in between two meshes. So it gives us a problem if we want to apply KVL to each of the mesh. Right? It gives us a problem. So what do? In super node, we combine the two nodes as one. In super mesh, we combine the two meshes as one. Simple as that. So both of them, they have similar procedures. They just you just change voltage to current and vice versa. So let's designate this as I1 and have mesh current I2 here and mesh current I3 here. Right? So mesh 1 and mesh 3, they are having a current source in between them, so I'll take it as a super mesh. So let me use another color to do that. So this is the super mesh. Right, so that's the super mesh. So yeah, so let me write the equation for mesh 2. So applying KVL to mesh 2, what do we have? We have 2i2, right? This here is 3 ohms. So plus 3 into bracket i2 minus i3. You can see that the 3 ohm is in between i2 and i3, and the current is going in the direction of i2, but i3 is going in the opposite direction. So plus 1, we also have 1 here, 1 into bracket i2 minus i1 equals 0. Right, so if I should rewrite this, I will have minus i1 plus 6i2 minus 3i3 equals 0. That's equation 1. Always remember, we have 3 meshes, and therefore we are looking towards 3 equations. 3 equations. So the super mesh. So first thing you should write the super mesh equation. The super mesh equation. So the super mesh equation is the KCL along this path, along this node. So I1 is going downwards, the same direction as 7 amperes, but I3 is going in the opposite direction to 7 amperes, and therefore the super mesh equation will be what? I1 minus I3 equals 7 amperes. I1 is going in the same direction, right? So I3 is going in the opposite direction, which means that if you subtract I3 from I1, it will give us 7 amperes, and that's our second equation. Then applying KVL to the super mesh. KVL to the super mesh. So applying KVL to the super mesh. So from 7 volts here, you can see that it will enter from into the negative. So we have minus 7 volts. Then when it gets to 1, it will be what? Plus 1 into bracket I1 minus I2. Right? Then when it gets here, it goes through 3. So everything is now is just a mesh, just one mesh. So we've removed this. Right? Everything is just one mesh. So then plus 3i3 minus i2. How do I know it's i3 minus i2? The current, the way I'm reading it is clockwise, right? So when I got here, i3 is going in the same direction, right? But i2 is going in the opposite direction. That's why it is i3 minus i2. Then when I get here, it is what? 1 multiplied by i3, and therefore is equals to 0. That's it. That's the third equation. If I'm to solve these 3 equations, what do we get? So we have 3 simultaneous equations. The first one is minus I1 plus 6I2 minus 3I3 is equals to 0. The second one is I1 minus I3 is equals to 7. And the third one, if I should write the third one, I should have I1, right? I should have I1, then I should have minus 4I2. Then I should have plus 4i3 equals to 7. Equals to 7. So that's equation 3, right? So if I solve the 3 equations, what will I have? So solving the equations using calculator, I have I1 is equals to 9 amperes. I2 equals 2.5 amperes. and I3 equals to 2 amperes. So as you can see, it is very simple to solve. So what do you do? First thing is determine if the circuit is a planar circuit, count the number of meshes, then if the circuit contains current sources shared by two meshes, so you have to form the two meshes as just one, and it is called a super mesh. Then you write KVL equation around the meshes that are not super mesh, and of course write the super mesh equation and apply KVL also to the super mesh to get all your equations right. So if you have 5 meshes, you are looking for 5 equations. Your super mesh will take what? 2 equations. Therefore, organize your equations and solve the system of equations for the mesh current. And after that, you can get any variable of interest the question is asking you to get. That is very simple. And if you have any question, you can drop it in the comments, and I'll make sure that I give you a very satisfiable answer. Thank you very much. This is the end of our nodal analysis and mesh analysis topic, and the last thing I'll be talking about is nodal analysis versus mesh analysis. What is the comparison between the two? Now that we have examined two distinctly different approaches to circuit analysis, it seems logical to ask if there is ever any advantage to using one over the another. If the circuit is non-planar, then there is no choice. We have to use the supernode, provided that we are indeed considering the analysis of a planar circuit. However, there are situations in which one technique has a small advantage over the other. If we plan to use node analysis, then the circuit with n nodes will need to n-1 KCL equations. That is, if we have 6 nodes, we're looking for 5 KCL equations. Each supernode defined will further reduce this number by 1. If the same circuit has m distinct meshes, then we will obtain at most m KVL equations. Each supermesh will reduce this number by 1, and based on this fact, we should select the approach that will result in a smaller number of simultaneous equations. The more the simultaneous equation, the more difficult it is for you to solve. The highest I've seen in normal scientific, like I said, in normal scientific calculator that can be allowed in an exam hall to solve is 4 simultaneous equations. For example, if you are now given a circuit with 6 nodes or with 6 meshes, so how will you be able to reduce it to 4 so that you can use your calculator? So that is where it comes into place. So we have to select an approach that will result in smaller number of simultaneous equations. So what about the situation where a dependent voltage source is controlled by a current, or the converse? That is where a dependent current source is controlled by a voltage. So provided that the controlling quantity can be easily related to mesh currents, we might expect mesh analysis to be more straightforward option. But likewise, if the controlling quantity can be easily related to nodal voltages, nodal analysis may be preferable. One final point I will be making mention in this regard is to keep in mind the location of the source. Current sources which lie on the periphery of a mesh, whether dependent or independent, are easily treated in mesh analysis. Voltage sources connected to the reference terminal are also easily treated in nodal analysis. But when those voltages are connected in between non-reference nodes, that's where the problem of supernode occurs, and I've already explained in the last tutorial how you can tackle that using supernode analysis. With this much elaborate explanation, I'm very confident that you are able to solve questions and apply supernode and supermesh analysis to the circuit you are given. Like I said, if you have any question, drop it in the comment section, and I will see you in the next tutorial. Thank you.